students, a very warm welcome to you all. So, I hope you have revised the concepts of biomolecules. It's a very important chapter indeed. But I would like to tell you over here that we are going to discuss the JEE main pattern exercise. JEE mains does not have as much weightage of biomolecules as it can be, but yet we are going to discuss a questionnaire related to biomolecules as per the JEE main pattern as well. So, let us just move on to the question number 1. What do you have? So, which of the following bases is not present in DNA? So, you must be having a proper knowledge of DNA. So, let us just try to recall that. So, DNA contains what? It has got two kinds of bases, that is purines and pyrimidines. So, I have got purines as well as pyrimidines. And under the category of purines, what do we have? We have got adenine and guanine, A and G. And under the category of pyrimidines, we have uracil, cytosine and thymine. But here in the DNA, uracil is not present, but these 4 bases are present. So, as per our knowledge, as per our information, can we correlate it with this question? So, quinoline, adenine, cytosine, thymine, which is not present, they are asking. So, adenine is there, cytosine is there and thymine, that means A, C, T. But whereas quinoline is not a base but an alkaloid. So, quinoline is an alkaloid and it is not at all present in the DNA. It has nothing to do with the DNA. So, I hope everybody has got the answer, which is A. So, let us move on to the next very question. So, the next question is, now it is quite important question here, as it actually asks us about a particular test that is given by what? So, which of the following compounds can be detected by Molish test? So, you need to have a proper information about Molish test. It is a pretty beautiful kind of a test. Why? Because we take up the solution of the concerned compound out of the 4, which is the right answer. So, I am taking up the solution of that compound. I add up what? I add up, let us just remove that first. Okay, now what is Molish test? First, I take up the compound solution plus I add up the alpha naphthol solution. So, I have got alpha naphthol solution. I add up, I mix up the two. Then what do I add is into the test tube. I have taken these two things in a test tube here. So, what happens? I then add up a few drops of concentrated sulfuric acid here. So, that is conc H2SO4 and that too sliding onto the sides of the test tube. So, I need to slide down the drops over here. What will happen? A beautiful violet ring will appear like that. So, a beautiful violet ring will be appearing in the test tube, confirming what? Confirming the presence of carbohydrates. So, the Molish test is always for the carbohydrates. So, another kind of a very informative question it is. That means Molish test always is used for the detection of sugars, or we can say the carbohydrates in turn. So, I hope everybody is clear with the test here. So, you need to remember this very test particularly. Let us move on to the next question. So, what do I have? So, I have got the presence or the absence of hydroxy group. On which carbon atom of sugar differentiates RNA and DNA? So, they are actually asking about what is the difference between the structure of RNA and DNA. So, let us just try to make it out. So, we all know that RNA is a ribose nucleic acid and DNA is ribose nucleic acid. and whereas the DNA is, that is deoxyribose nucleic acid, so that is deoxyribose nucleic acid. That means what do we have? We have got a pentose sugar here. So we have got a pentose sugar. That means both are pentose. I just need to have a deoxy part. That means I am removing one OH group. So that is what it needs to be. And if you observe over here, what is the actual sugar present? It's beta D ribose. Whereas in this case, it's beta 2 dash deoxy. It is also deoxyribose. So first let us just find out what ribose is. So ribose is actually aldopentoses. So ribose is aldopentoses. That means having 5 carbon atoms. So in the case of beta, that means the anomeric carbon, it would be having OH towards upper direction. And so where do we start from here? We started from this very side, OHH, and over here it would be, okay, now let me just make this a bit different. I need to have a D. That means it would be lying towards right. And as I told you in my sessions, if you have followed up my sessions, D means whenever I am having an open chain structure, it would be, the OH would be lying towards the right hand side. That means this very side. So it must be represented downwards whenever I am drawing the cyclic structure. So that is how it needs to be. And this is nothing but the beta D ribose. So we have got the structure over here. And in order to have beta 2 dash, that means what? First, second. So that would be the second carbon atom. So here on the second carbon atom, I need to replace this OH. That means I need to have a deoxy part. I am deoxidizing it. That means removing this OH part. So that is what here it needs to be. The remaining structure would be the same, but here it would be, instead of OH, it would be H. So that is what the sugar is included in the DNA. So let us just make the remaining ones. So that is what we need to have over here. So let us just analyze the question, the presence or absence of hydroxy group. So they are actually asking the absence of hydroxy group. So we have got absence, not the presence. That is the first thing that we have confirmed. And they are asking about onto which carbon atom it is actually absent. So here if you look, it is very much evident from the name itself. But still, in order to have a proper clarity, I have drawn the structures as well. Onto the second carbon atom, there will be a difference of OH group. So let us just mark out our option. It is B. I hope everybody has got it. So now let's move on to the next very question. So it is, yes. Oh, here the question comes about the proteins finally. The secondary structure of protein refers to. So I need to have a proper information about what primary protein is, what secondary is, and what tertiary is. So we all know that primary is just depicting a chain of different amino acids linked together. So that is a single chain, and that single chain is containing different amino acids linked. And what about the secondary? Secondary now comes up with more structures. That means a different kind of a representation of this straight chain, of this sequence of amino acids. So basically it represents sequence of alpha amino acids, whereas the secondary one has got what? Has got two types of structure formed. Now this chain getting developed into a structure. That means we have got first is helical structure. So we have got a helix, and these are the different amino acids. And also we have got the beta pleated structure, something like that. That means we have got the answer. In the secondary structure, we have got alpha helical structures, alpha helix, and beta pleated structures. So I hope everybody is able to recall the concept over here. Let us just mark out our option. So it's alpha helical backbone. They're asking about the secondary structure. So alpha helical backbone, hydrophobic interactions. It is not hydrophobic. Sequence of alpha amino acids, no. It is represented by the primary. Fixed configuration of the polypeptide. So that is not also the case. Fixed configuration may or may not be there. So what do we have? A as the answer. I hope everybody has followed up. So let's just move on to the next very question. What do I have? Now again a pretty simple question. So I have got the term anomers of glucose refers to. So we all know what anomers are. So let us just have a look at the options. Isomers of glucose that differ in the configurations at carbons 1 and carbon 4. So they are asking about carbon 1 and 4. That is not anomers, but this is epimers, if you are able to recall. A mixture of D-glucose and L-glucose, also not the case. Because D and L, that means OH, which is to the last. If I draw the structure for glucose, that is glucose that I am drawing over here. So in order to have a proper configuration, that means here I would like to represent the configuration, that is, this is D-glucose. And what if I have this OH towards the left? Then it would be L-glucose. It is not anomer but a proper configuration. So here it is a configuration. So this is also not the option. That was not. Enantiomers of glucose, not at all. The enantiomers will be only these. D and L could be the enantiomers. So this is not the case. Isomers of glucose that differ in the configuration at carbon number 1. Yes, that is our option. So let us just see how. So if I have a structure of glucose like that, and let us just make the glycosidic linkage. So the glycosidic linkage will be somehow like this. And let us just connect the two. So if I connect the two, what do I get? A glycosidic linkage, something like that. So that is how I am going to make it. And if this OH now lies towards the right, so this is C1. This is nothing but the anomeric carbon. We have already discussed this. And this is C1. If OH is lying towards the right, we get the alpha anomer. And if this OH is lying towards the left, we get what? Beta anomer. So that is related to the anomeric carbons that we have. I hope everybody is getting me. The term anomers of glucose refers to the isomers of glucose that differ in the configuration at carbon number 1. It will always be carbon number 1 for anomeric carbons. For epimers, it could be different. So that is the difference. So I hope everybody has got the answer right. Let's just move on to the next question. What do we have? Now comes up the question related to enzymes. So I hope everybody has revised the concepts. So identify the correct statement regarding the enzymes. Enzymes are specific biological catalysts. Yes, they are. That can normally function at very high temperatures. Approximately they have given 1000 Kelvin. So is there 1000 Kelvin temperature developed within our body? Not at all. Also, the enzymes lie in our body, they function properly. That means what? They can actually exist, they can actually perform their activities within normal, within mild conditions. They do not require so much of temperature, because so much of temperature in our body would be leading to something else. We would be dying. So, this option is incorrect. I need to find out the correct statement. Just be very careful with the question. Second is, enzymes are normally heterogeneous catalysts and are very specific in their action. So, do you find this very statement true? What is heterogeneous catalyst? That means they may be present in the other form within our body. But if you see, our body has what? Mostly the liquid state. It has got the liquid state, and the enzymes need to be performing their actions within that liquid state. So, they actually not maybe, but they must be lying in the same very state. That means they must be lying in the homogeneous state. That means this very statement is incorrect again. Enzymes are specific biological catalysts that cannot be poisoned. They can definitely be poisoned. So, if you have read about the chapter of chemistry in everyday life, there is a lot of things, there are a lot of medicines which are available actually, which actually try to modify the function of that enzyme. That means we are poisoning the enzyme within the body in order to treat a proper condition, or in order to alter the way of that enzyme. So, remember having allosteric sites. So, whenever a drug actually attacks on the allosteric site of the enzyme, it modifies its active site, the shape of the active site, and what will happen? The activity of that enzyme is modified. So, they definitely be poisoned, they can be poisoned. That means this statement is incorrect, can be poisoned. So, I hope everybody has got this very point. Now, let us move on to the last. Enzymes are specific biological catalysts. Indeed, they are, that possess well defined active sites. Yes, a specific enzyme has a specific active site for a specific substrate. That what Locke's and Key model says. So, I hope everybody has recalled the concept, and this is the very correct answer over here. So, now let us move on to the next very question. So, what does the next question say? The reason for the double helical structure of DNA is the operation of. So, I need to find out what kind of a force is existing between the double helical structure. What is a double helical? Something like this. So, that is what the double helical structure is, and I need to have some bases in between, A connected with T, G connected with C, G connected with C, A, T, 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 A, G, A, sorry, it would be A, and so on. That is how we need to have. So, these are the two helical structures, two secondary structures of proteins. One is this strand and the other is the yellow one. So, actually these two strands are getting connected to form a DNA. So, how these strands are connected, that is the question. So, we all know that A binds with 2 kinds of bonds with T and G binds with 3 kinds of bond with C. That means what? What are these type of bonds? These are nothing but the hydrogen bonds. So, we have got H bonding over here. So, let me just complete it out. So, it would be 2, it would be 3, again 3, again 2, 2. It's just a random sequence that I have. So, that is how the DNA gets connected. The two strands get connected via hydrogen bond. So, let us just find out our option. Van der Waals forces, no. Dipole-dipole interaction, not at all. I have got the hydrogen bonding over here, and that is our answer. I hope everybody has followed up. So, now let us just move on to the next. Yes, complete hydrolysis of cellulose gives. So, remember the structure of cellulose. What does it actually contains? So, cellulose is actually having a beta D glucose and a connection between what? Again a beta D glucose. So I've got a beta D and a beta D. And one beta D glucose is connected via carbon 1 and the other one is connected via carbon 4, and that is how the connection is made. So let us just have the structure first. So the structure is, I am making the two glucose molecules here and I need to make a beta, that means OH on the upper side. That is how I am going to make it. This is what? This is carbon number 1. So that is carbon number 1. I need to have a proper glycosidic linkage between the two. Again a beta D glucose molecule. And over here there would be the connection. That is how we are going to make the cellulose. So it would be like this. So that is the connection, and these kind of molecules will be connected and the chains would be formed. So this is nothing but the basic molecule of cellulose. So upon the hydrolysis of cellulose, that means I am breaking the molecules into the monomers. So what kind of monomers will I be getting? Is it D-fructose? No. D-glucose, D-L-glucose. So what will I be getting here is not D-fructose, not D-ribose. Out of D-glucose and L-glucose, what will it be? We have already done this. It is D-glucose every time. So just be very careful while choosing the options here. It would be D-glucose as the answer. I hope everybody has got the answer right. So let's just move on to the second last question. What do we have? Okay. Monomers are converted to a polymer by. So the question actually resembles the chapter polymers, but still yet it has a meaning in this chapter as well. So the monomer is always converted into a polymer. What kind of a monomer and what kind of a polymer we are dealing with here in the biomolecules chapter is the peptide linkages, or we can say the peptides are converted into polypeptides. So how are these polypeptide chain formed? They are formed by when specific amino acids they get combined, and how they are combined? They are combined by condensation, or I can say removal of water molecule. So if I take an example of glyala, how does it form? So it forms, or if I say two glycine molecules are connected, let us just have glyala first. So it would be, okay, let me just write it again. So I am connecting the two. So it would be something like this, the glycine would be something like this, and let me just make the alanine. So that is alanine here, and we need to make a polymer, we need to make a polypeptide. So I need to have several peptide bonds in that very chain. So I would be condensing the two to make it attach. That means loss of water molecule. That is how it is going to get a loss. Let me just make it again. So it would be OH, and there will be a loss of water molecule minus H2O. That means leading to the condensation and forming. That is how different kind of amino acids get connected via condensation process and give a polymer or a polypeptide. So that is what we have over here. It would be glyala. and so on and so on. So that is how the connection is made. I hope everybody is clear with it. So monomers are converted to polymer by hydrolysis of monomers? No. Hydrolysis means breakdown, condensation reaction between monomers. Yes, this is the answer. Protonation of monomers, none of the above. So none of the options, the last two are correct, but B is. I hope everybody has got the answer over here. Now let's move on to the very last question. What do we have? A substance forms Zwitter ion. It can have functional groups. So what is a Zwitter ion? Whenever a compound is containing a basic part as well as an acidic part. So how does the Zwitter ion actually gets formed? So if I take up this very case, this is nothing but depicting the amino acid. So let us just try to make this Zwitter ion here. So it would be, okay, if I take up alanine, COOH. So what happens is, this is a base, it has got electrons to donate, so that is a base. That is an acid, that means it can donate its proton. Where the proton goes? Onto these electrons. So what kind of an ion we get? We get a Zwitter ion over here. That would be somehow like this, having positive as well as the negative charges. So we have got this option right, but if you see at the B option, I have got sulfonic acid. So can the presence of sulfonic acid can also be forming a Zwitter ion? So let us just see. Yes, definitely it can also be a Zwitter ion formation in the case of sulfonic acid. So here, if again I take up similar kind of a molecule, NH2 and SO3H. Again this acid is capable of donating the H positive. So what do I get here? Again I get a Zwitter ion, NH3 positive, SO3 negative, H and CH3. So in this very case also we can form the Zwitter ion. So that is how the Zwitter ion is made whenever we have acid as well as the basic part within a particular molecule. So it can have positive and negative charges developed. So that is how we are going to find the isoelectric point as well in the case of amino acids. So I hope everybody has got it. This is also can be the case, but that means both A and B is a correct option. I hope you have got the answer over here. And I hope you have liked the questionnaire round. It was pretty easy, not a big deal, not very tough. So you just need to practice all of those once again to have a proper hold over the subject. I'll be dealing with the biomolecules advanced in the next session. Till then, have a good day.